Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, our mission is to transform some of that destructive hate energy into constructive love energy. And mathematics is part of all that surrounds us. Just pause and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over. Now let's get down to some serious math. This is a continuing series on algebra, and specifically this will be video 5 of the series, and it's a continuation from video 4. Let's have a look at question 14. It says simplifying rational expressions, aka fractional expressions with restrictions. And this type of problem will involve addition and subtraction. And specifically, they're LCD problems, lowest common denominator problems. Okay, sometimes I'll write LCD in lowercase, sometimes I'll write it in uppercase. I guess it depends on how I feel that particular day. So, but LCD means lowest common denominator, and that's the essence of addition and subtraction problems when dealing with rational expressions. Let's look at part C over here. We have 1 all over x squared plus 3x minus 4 plus 1 all over x squared plus x minus 12. Of course, we identify this as a rational function. The denominator over here is quadratic. This is also a rational function. Denominator is quadratic. The difference from other problems that we looked at is that now we have a plus sign. So essentially we have two clusters over here. We don't have a single cluster, but we have two clusters. If this plus sign were to have been a multiplication symbol or a division symbol, then these would be identical to the ones already that we've already looked at in video number 4. Okay, but these are substantially different, so the procedure is different for these. The idea, first of all, is to examine each cluster and to factor each cluster. Okay, we can certainly factor that quadratic on the bottom. It factors as 1 all over x minus 1, x plus 4. Easy to verify that that expands to x squared plus 3x minus 4. You can try it out on your own. And then we have x squared plus x minus 12. It easily factors as x minus 3, x plus 4. Again, you can expand to verify. And the idea now, after we've done the factoring, is to be able to identify what the lowest common denominator is, the LCD. Well, we know we need an x minus 1 because it appears there. We also know we need an x plus 4 because it appears there. Notice that we need an x minus 3 because it appears in the second cluster. And it appears that we need another x plus 4, but not really because we already counted x plus 4 once. So the bottom line is that the LCD is x minus 1, x plus 4, x minus 3, and x plus 4 is redundant, so we don't need it. So again, the LCD for this problem is x minus 1, x plus 4, x minus 3. And then what we do is, this is the way I like to add fractions. You put a big division bar down, write the LCD down, just drop it down in the denominator, and then look at the numerators. You do 1 dot empty bin, just leave it empty for now, plus 1 dot empty bin. Okay, now the idea is to be able to fill in the bins, we have to do LCD divided by the original denominator. When you do the LCD divided by the original, what's left over here is an x minus 3. Or another way to look at it is this. When you look at the original denominator here and compare it to the LCD, what's missing here? What's missing is the x minus 3. Again, when you compare this to this, what's missing is that guy. And this guy over here gets put inside the bin. And then plus 1, again, we have an empty bin over here. When you compare the denominator here with the LCD, what's missing is the x minus 1, so you drop it inside the bin. The next step is to expand the numerator. Do not, I emphasize, do not expand the denominator. You want that in factored form. Never, ever expand the denominator. You only expand the numerator to simplify it. That's the only reason why we expand the numerator, because this can be simplified through expansion. When you expand, you get an x minus 3 plus x minus 1. When you collect like terms, you get 2x minus 4. And that's illustrated in the next slide. Okay, so we get a 2x minus 4. That's the LCD on the bottom. We can factor out from the numerator. We can factor out a 2 in the numerator. So the GCF is 2 in the numerator. So we factor it out. And we get a 2 bracket x minus 2. And then the LCD is just a copy paste. Now this appears to be the end of the problem. Notice no cancellations at all, top to bottom cancellations. And there were no cancellations done previously. No cancellations whatsoever. So now we have to impose the restriction. For the 0 over 0 restriction, we're always looking for cancellations. But of course there were none. So nobody goes to jail. Now we look for 1 over 0 restrictions. Of course, if we look for 1 over 0 restrictions, we always look at the end of the problem. We look at the denominator specifically. We want to make sure that denominator is never equal to 0. We don't care about the numerator. We only care about the denominator. Okay, that 1 indicates the numerator. We don't care about that. It's the 0 in the denominator that we care about. That 1 is just symbolic. That 1 could be a 10. It could be -2. It could be anything but 0. Okay, so the 1 is symbolic, but the 0 on the bottom really is a 0. So to ensure that this is not equal to 0, you have to ensure that each factor is not equal to 0. And that's why do not expand. You want to leave it in factored form, because you want to make sure that that's not equal to 0. That's not equal to 0, and that's not equal to 0. Okay? So if x minus 1 is not equal to 0, that means x cannot be equal to 1. If x plus 4 cannot be equal to 0, that means that x cannot be equal to -4. If x minus 1 cannot be equal to 0, that means that x cannot be equal to 3. So there are 3 vertical asymptote restrictions, which if any of these restrictions are violated, then somebody dies. Okay, and we certainly don't want that to happen. So to recap, the original expression that appeared on the other slide is equivalent to this expression, provided we impose these 3 restrictions, which are vertical asymptote restrictions. Okay, so we don't want anybody dying, therefore impose these restrictions. Let's go on to the next slide. Okay, this is a more complex problem. Again, you always, whenever you're doing mathematics, always take a global view, bird's eye view of the problem. Do not look at little details. Okay, you have to look at the entirety of the problem, the entire problem. When I look at this from a bird's eye view, I see a plus sign there, I see a multiplication sign there. So we have a cluster over here, and this is another cluster over here. What we're going to do is simplify each cluster. Okay, the first step is to factor all. If we examine this cluster over here, 2b minus 5 is linear, so that just gets dropped down. There's nothing to factor. The denominator over here is quadratic in b, so it easily factors as b plus 3, b minus 5. You can verify that. Over here, the 3b just gets dropped down. And this quadratic over here easily factors as b minus 5 times b plus 6. This is a quadratic over here on top, easily factors as b plus 2, b plus 6. And of course, b plus 3 is linear. You just do a drop down. And now, before you even think about joining these 2 clusters together, because at some point we're going to have to join the 2 clusters together, what you have to do is do any internal cancellations. Internal to the cluster. If I look at this cluster over here, nothing cancels. If I look at this cluster over here, we do get some cancellations over here. I look to cancel out a B. I don't see it on the bottom, so B remains. 3 remains because I don't see any 3's on the bottom. B plus 2, I don't see it on the bottom, so that remains. But B plus 6 gets canceled with B plus 6 on the bottom. So you have to take note of that cancellation. Okay, we need that. You have to make a note of that, and that's why I indicate cancel all. So you know exactly where to go to look for the cancellations that you did previously. So now, after we do the cancellation, this is just a drop down with nothing to do. When B plus 6 is canceled, what remains on top is 3B bracket B plus 2. What remains on the bottom is B minus 5, B plus 3. Okay, so now we've got something that's manageable. At this point, it becomes an LCD problem. Okay, because whenever you're adding two fractions, you have to find the lowest common denominator. So in the LCD, we definitely need a B minus 5. And we definitely need B plus 3. And you know what? I just noticed over here that we have a B plus 3, B plus 3, B minus 5, B minus 5. So we already have a common denominator. Okay? We already have a common denominator, and the common denominator is B minus 5, B plus 3, or the other way around, B plus 3, B minus 5. It doesn't really matter the order that you put the factors in. That means when we already have a common denominator, like for example, if we have 3 over 4 plus 7 over 4, we already have a common denominator, so all we do is do 3 plus 7, which is 10, all over 4, and then reduce. Okay, so all we have to do now is just add the numerators. So there's the 2b minus 5, and there's that numerator there, and we drop the common denominator down there. At this point over here, we expand the numerator and only the numerator. Never expand the denominator. Never get tempted to cancel anything at this point before expanding the denominator. Okay, before expanding the numerator, sorry. Okay, the denominator never gets expanded. Only expand the numerator. When you expand the numerator, you get 2b minus 5, then 3b squared plus 6b. Then you have to collect like terms in the numerator. The denominator just comes down, it just gets dropped down. And then we'll go on to the next slide. When you continue simplifying the numerator, it simplifies as 3b squared plus 8b minus 5. And the denominator, again, is b minus 5b plus 3. You can check this. This is a quadratic in B. It might factor. If it does factor, then you actually have to factor it. Okay, so if it did factor, you'd have to factor it and then look for any subsequent cancellations. But it turns out that this particular quadratic does not factor. And again, we'll get into more about factoring quadratics in another video. Just take it from me at this point in time. This factor in the numerator does not factor. And so the final answer becomes 3b squared plus 8b minus 5 all over b minus 5b plus 3. And we designate this to be the end of the problem. And now we have to impose the restrictions. If you recall in the last slide, here, let's go to the last slide. Do you recall that the b plus 6 was canceled? That means we have a cancellation restriction. So b cannot be equal to negative 6. At the end, we have to make sure that the denominator is never 0. Okay, we have two factors. We have to make sure that that factor is not 0 and that factor is not 0. When you put b minus 5 not equal to 0, you get b not equal to 5. And when you put b plus 3 not equal to 0, you get b is not equal to negative 3. So you have, at the end of the day, you have one whole restriction and two vertical asymptote restrictions. Again, these restrictions must be adhered to. Otherwise, you either go to jail or you die. Okay, They have to be adhered to. If you were being marked on a problem like this, like on a test, let's say you were given a problem like this on some test that you were writing, they would give you half the marks for this part, which is the reduced form, and probably half the marks for the restrictions at the end. Okay, so keep that in mind. No restrictions means you only get about 50% on this problem if you get the reduced form correct. Okay, because you omitted the restrictions, you will not get full marks. That's for certain. And I'll bet you get something like a 5 out of 10. Okay, let's go on to the next slide. And I think what we're going to do is do an over and out at this point. And thanks to all for viewing this video. Stay tuned for many more videos to come. If you like the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out for Math Lab Tutorials in Toronto.